Hi there, welcome. Have you ever wondered what curve best describes the shape of an electric power transmission line? It's called a catenary. Catena is Latin for chain, as the catenary is also the shape a chain will take when suspended in free air, fixed only at the endpoints. The catenary is mathematically described by one of the three hyperbolic functions, the so-called hyperbolic cosine. But what is hyperbolic about the catenary? And why do we call it a hyperbolic cosine? Let's find out. To know what we're talking about, we start with the definition. The hyperbolic cosine is defined as half the sum of the standard exponential function and the exponential that is its mirror image with respect to the y-axis. The definition of the hyperbolic sine looks a lot like the hyperbolic cosine. The only difference is a minus sign. And a hyperbolic tangent is the quotient of the hyperbolic sine and cosine, just as you would expect from regular trigonometry. As you can see, hyperbolic functions are built up entirely from simple exponential functions, so we can easily get an idea what their graphs look like. Being the sum of two functions that are each other's mirrors image, the graph of the hyperbolic cosine is symmetrical with respect to the y-axis. But, as you can see, it looks in no way like the graph of the cosine. It's not even periodic. Perhaps the shape reminds you of a parabola, but closer inspection reveals that it goes much faster to infinity than any parabola. Indeed, for large positive x values, the negative exponential becomes negligible, and the hyperbolic cosine acts almost like a single exponential function. The graph of the hyperbolic sine can be understood in much the same way. Its behavior for large positive values of x is dominated by the positive exponential and quickly becomes indistinguishable from the hyperbolic cosine. For negative values of x away from the origin, the graph behaves as a descending exponential function. A striking difference between the hyperbolic sine and cosine is their symmetry or parity. The hyperbolic cosine is symmetric with respect to the vertical axis, indicating it's an even function, whereas the hyperbolic sine is symmetric with respect to the origin and is hence an odd function. Last but not least, let's take a look at the graph of the hyperbolic tangent. We see the graph of the hyperbolic tangent has two horizontal asymptotes, y equals -1 and y equals 1. Like the hyperbolic sine, it has a point of inflection in the origin. Note that of these three functions, only the hyperbolic cosine has an extreme value. Those are pretty looking curves, but we still don't have a clue why we call these functions sine, cosine, and tangent. There are several reasons for this, and we will not explain all of them, but we can give you a hint. Let's start by calculating the derivative of the hyperbolic sine. We insert the definition and put 1/2 up front. We take the derivative of the exponentials, and we recognize the hyperbolic cosine. That looks familiar, doesn't it? Let's derive another property. Here we start out by calculating the difference of the squares of the hyperbolic cosine and sine. Again, we substitute the definition. Next, we expand the squares for the magnitudes within the brackets. And we clean up a little bit. Hey, does this ring a bell? Let's compare the results in a table. The derivatives of the hyperbolic and trigonometric sine look formally identical. And these two look very similar as well. They only differ in the sign. We give one addition formula for free, without derivation. Again, they look almost identical, only the sign is different. In class, we will show you many more interesting links between trigonometric functions and their hyperbolic counterparts. But I hope to have made the case why these functions bear similar names as the trigonometric functions. But why are they called hyperbolic? To see this, let's go back to the unit circle. A point on the unit circle has coordinates cosine t and sine t. And since the sum of the square of the cosine and the square of the sine is always 1, we can see that points with coordinates cosine t and sine t lie indeed on the unit circle. That is why trigonometric functions are sometimes also called circular functions. They can conveniently be used to parameterize a circle. Now, to show that the curve formed by all points with coordinates hyperbolic cosine and hyperbolic sine is indeed a hyperbola, it is sufficient to show the difference of the squares is equal to 1, as x squared minus y squared equals 1 is the standard form of a hyperbola. But we already did show this fact. Okay, so from now onwards, you will always remember that hyperbolic functions are useful to parameterize hyperbola. Okay, that is all very well, but perhaps you ask yourself the one question that mathematicians sometimes don't. What is it good for? Hyperbolic functions are encountered in many different contexts, such as in the construction of arches, the design of buildings, as a threshold function in machine learning, in the optimization of transmission lines, and in the description of minimal surfaces, such as in this soap film. There are in fact still many more examples, but there's one fundamental application that I simply cannot withhold from you. Galileo Galilei observed that a falling object on a ship seems to fall in the same way with respect to the ship as an object on land would fall to the ground. Now, the inescapable consequence is that velocity is relative to the observer. Indeed, to an observer standing on the coast, the object on the ship would fall as if it had a velocity equal to the vector sum of the velocity of the ship with respect to the land and the velocity of the falling object measured with respect to the ship. And this is historically the first known formulation of the principle of relativity. In one dimension, we can write this simply as v equals w plus u. Einstein realized that things get more complicated if the velocities involved are no longer negligible in comparison to the speed of light. In this case, the simple addition formula needs to be replaced by the more complex formula v equals u plus w over 1 plus u times w over c squared, where c is the speed of light. Now, to see what this equation means, let us first rewrite all velocities relative to the speed of light by dividing left and right by c. Take a look at it. We see that as long as u and w are smaller than the speed of light, so is v. In particular, you may verify that if both u and w are equal to c, v is also equal to c. Can you see why? That's right. Both the numerator and the denominator are equal to 2. So v has to be equal to c. Now, it is of course inconvenient. We can no longer simply add velocities, but hyperbolic functions come to our rescue. Take a look at the addition formula for the hyperbolic tangent. As you see, the formal similarity between the two is striking, and this suggests the following idea. If we substitute the relative velocity v over c in the first formula by the hyperbolic tangent of a yet unknown quantity v tilde, and likewise for u and w, we get, and substituting, we obtain the following formula. But according to the hyperbolic addition formula of the tangent in the upper right of the screen, this is equal to the hyperbolic tangent of u tilde plus w tilde. So we finally obtain, ta-da, v tilde equals u tilde plus w tilde. Now, the quantity v tilde is called the rapidity associated with the speed v. So, although we can no longer simply add velocities in a relativistic setting, we still can add the corresponding rapidities. Isn't that a beautiful idea? I hope you have an idea what a hyperbolic function is and why it can be useful. In class, you will learn more about these interesting functions. See you there.